a volumetric charge density that they say we can use rho to describe, correct? And it's all negative. Now, let's start by considering just looking at it like down the center. So, and they give us a picture of this to look at too. Looking down the center, if I was to try and figure out what's happening with the center of the wire here, what do you think the electric field would be at the very center of this wire? I mean, zero. That shouldn't be a hard decision to make. There's negative charge all around you. If you're at the exact center of this wire, it should be zero. If I put a Gaussian surface at the center, how much charge could it enclose if it's at the center? Think on it for a minute. It can't enclose any. So if it can't enclose any charge, there's no electric flux. It doesn't mean no electric field, but because of the symmetry, it's highly likely that there's no electric field. But if you don't like that, then use your basic knowledge of opposites attract and like charges repel. If I try to place a charge right here at the center, then it's going to be pushed in all directions equally. It'll experience no net electric field. Now, how many of you can kind of see in your mind that as I create a Gaussian surface that expands from the center, that Gaussian surface is going to kind of collect more and more charge? Do you guys see that? That this volume, and if I put this little volume, say right here, and if that's my volume, because that's my Gaussian surface, that everything inside here will be the charge that is enclosed. And that will tell me what the size of the electric flux is. And as R gets bigger, as this radius gets larger, I will be enclosing more and more charge, until such time that my surface is as big as the wire itself. Any point after that, then I don't enclose more charge, but my surface area will keep getting bigger and bigger. Does that make sense so far? Any question about that yet? So I see two ranges to which I should do this problem. I think I should do this problem with a radius of my Gaussian surface that starts from 0 and goes to the radius of the wire. And then I got to do the problem a second time for when my radius of my Gaussian surface is outside the radius of the wire. When we deal with a problem that has something like this, a uniform charge distribution that has full three-dimensional extension, we probably need to consider boundaries where we have to do the problem more than once. It doesn't really require us setting up the problem much. It does require us setting up the problem at least one time and using that setup twice. Now, just a couple of things that I didn't maybe make clear yesterday. How do we use Gauss's law to provide us with a useful solution? They're different. Why do we even have Gauss's law? Well, because in certain circumstances, Gauss's law can actually tell us what the electric field is. Now, just to keep this kind of idea going, you can make devices then that determine how much charge there is by their measurement of electric field. It's one of the ways we can tell when a cloud is about to shoot out a piece of lightning. We can measure the charge buildup, but we can't do it directly. We use Gauss's law to measure the electric field. So we can make an electric field detector you can stick outside. And by putting a bunch of them around, we can kind of get the collective charge density of the cloud as it passes by. They look for abrupt changes in that electric field. They know that that's where a lightning struck. By looking at the strength of the electric field, they know when a lightning strike is about to happen. So these aren't fake ideas. In fact, in a few minutes, when we get past this problem, we'll talk about why your cell phones don't work in here. It's explained by Gauss's law. It's not obvious why, from looking at Gauss's law, but you can explain it by considering Gauss's law. So let's work through this problem. I want to basically show you why it's the same as the other problem. I'm going to start with the smaller cylinder. So let me erase the cylinder that's here. And we're not on any special schedule today, right? For once, this is just the regular old schedule. True?
Isn't there the
Yep. Thank you. But I don't think we have a different schedule for it. I think that it's occurring at the end of one of our class periods. I just don't know which one. Anybody want to be able to tell me which one? Oh, good. So it's not this one. All right, so I am producing a cylinder that is, let's go with H long, and has a radius of R. I don't remember what the problem actually tells me, but I'm going to say that this cylinder has a radius of capital R. Is all that okay? What do you want to work on first? The flux side or the enclosed charge side? Because we have to do both sides, and we have to pick one to work on at a time. So which one would you rather work on? Flux or enclosed? Flux? All right, so we're going to do the flux portion first. We did this portion yesterday. Do you understand the symmetry is still the same? Because the symmetry is still the same, I'm going to imagine that the electric field is parallel and is traveling radial away from the center, which suggests an electric field that looks something like this in all directions. That good for you guys? Still has the same kind of symmetry. It's just that it's inside and outside, which suggests that when I consider the flux, I think I can break my flux up into the same three integrals as I did yesterday. So we'll take the circle away and have E dot dA for the top plus E dot dA for the bottom plus E dot dA for the sides. Questions about that? Like I said, we're choosing this because there's symmetry, and that symmetry tells me right off the bat that the top and the bottom give me zero contribution to the flux because there are no field lines that go through the top or the bottom. Even though it's surrounded by charge, that symmetry means that the lines themselves are traveling in such a way as they don't pierce the top and bottom. Looking at the sides, look, the area has got to be outward. That's got to be dA. Can you even see that little yellow arrow? Probably not. Let's go with, can you see this purple arrow? There we go. So that area has to be pointed outwards away from the center. The electric field is also outwards, suggesting that the electric field from the sides is going to be E dA cosine 0 degrees. Getting back to this part, I want to remind you this part is exactly the same as yesterday. It really is exactly the same as yesterday. The only thing that I keep trying to put out in front of you is that when we are coming up with the part that we actually have to integrate, our whole goal every single time will be the same. To try and bring E outside the integral and be left with something that just adds up the area. That's why we choose symmetrical shapes. So that all we have left is some integral that adds up all the contributions to the area. Now I know it's hard to read that right there, so you guys have this picture in front of you, right? I can just go to a new page. So remember, every piece of that blue line is the same distance from the center, and this thing has the same kind of symmetry that the line had before. It doesn't really matter that if we look at this picture over here on the side, the left side, it doesn't matter that there's charged pieces out here. Do they enclose any charge? So their portion, their collective part that deals with flux doesn't contribute here. And even if they did, do you realize that they have a symmetrical contribution? Which still means that at any one of these surfaces, the electric field has got to be the same because it's got the symmetry of how far away it is from the center. So we're looking at these pieces here. They all have to have equal electric fields because they have the same amount of stuff contributing to whatever the electric field is there. The only thing that you have to be concerned about is whether the direction of that electric field is in such a way to be in the same direction as the area. So if you're to split, say, if you're worried about that, say split this part, this piece of the cylinder in half. Right? I drew a tangent line to the curve at that point. Do you realize that by drawing that, there's symmetry that forces the electric field to have to be in that direction, which has to be perpendicular to that tangent line. If I do the same tangent line here, I get the same part, right? The same separation of charged pieces, making the electric field have to be this way. We don't have to think too hard about it. This is the way all of these are. We look for this symmetry so that we can use it this way. They're not going to give us a problem that doesn't at least have some amount of symmetry that we can use. This is the exploitable symmetry for this problem. Am I good to keep going? All right. We're really looking at a volume that's been enclosed. Can you guys see that? I want to know how much, volume of charge is inside here. To figure out how much charge that's going to be rho times the volume. This will give me charge. Rho is in coulombs per meter cubed. So all I need is the volume of that particular shape. Is greater than the radius. That means that my Gaussian surface is out here someplace. Is that okay? Do you realize that nothing about the flux portion of this changes? Absolutely nothing about that side changes. So when I look at the flux then, and that's this side, the flux side, I have epsilon naught times the integral of E dA cosine theta. This is going to be our flux. And again, the electric field is going to be uniform everywhere on that surface. So this becomes exactly the same as yesterday, which is kind of nice. I want to be careful here. Remember, this is the little r, so this is the radius of my Gaussian surface. Now, just for fun last night, I read the textbook. Read this chapter in a textbook. And by fun, I mean I just wanted to punish myself, apparently. So if you read the textbook, it's not terrible. It's not great. I'd consider reading the Halliday book. I think it has a better presentation. But the thing about this textbook's presentation is this problem is in it almost point for point. And they spend not any more time, but their pictures are better. So if you want to see different pictures of this, some methodically thought out, not drawn on the fly kind of pictures, take a look at your textbook in this chapter. And it's physics. All right, so that's the flux side. And I think we're okay to kind of stop there. That's how much electric flux there is with our little epsilon naught on the outside. So now we can do the other side, the enclosed charge. Now first, the enclosed charge isn't as nearly as hard as you might think. I think it was Jake yesterday who figured out that we only had to worry about how long the line was that was inside inside my Gaussian shape. Was it you who said that?
No, but I'll take credit for it.
Great, take credit for it. I don't usually say nice things to you, so there you go. Good job, Jake. We're pretty happy with that. In the case of this problem, though, and the volume of a cylinder. Do you guys remember what it is? I remember what it is. No, that's the surface area of the outside edge.
I'm willing to be reminded of it.
Okay. Pi r squared is the area of the top, or area of the bottom, times the height. That's how you find out the volume of any type of cylinder or stretched material. The volume of the top or bottom multiplied by how high it is. So that's the volume and then I have rho and that's it. This is the enclosed charge. The enclosed charge is usually pretty easy. So, taking it down to the bottom, rho pi r squared h. Now, we have done all the heavy lifting here. This is what it takes to figure out the electric field on the inside of this infinitely long cylinder. Do you see how much of this is just a rehash of yesterday? I would say 90%, maybe 80% for some of you who really are still struggling, which is probably all of you. But ultimately, at this point, all I have to do is solve this for the electric field. And I'm noticing right off that I get to cancel out pi here and pi there, h and h. And only one of the r's cancels, leaving me with an expression for the electric field that looks to be rho r in the numerator and 2 over 2 over epsilon naught. I think that's it. There's nothing else left. Yep, that's it. That's not very symmetrical. Now, a couple of points. What is the electric field when R is 0? That's what we expected, right? The electric field when R is 0 is 0. Now, when I said we get to reuse stuff, I really do mean that. So I want to consider the case where R is greater than the radius. I don't think we have any other work to do. First, when R back over here, the flux side is still going to be epsilon naught E 2 pi R H, because none of those things are different. R is bigger than the radius of the material, but that never mattered. Whether I was inside or outside, the shape is all that mattered. On the other hand, the thing that does matter is how much charge is enclosed, because the charge only extends to capital R. So when I write how much charge is enclosed, it's still just the volume. But now the volume stops at capital R. That's the only difference. So yeah, you're going to get equal amount of credit for doing part A and part B. But if you can do part A, part B is going to be a breeze. And you'll get all the same number of points. So now I cancel out the pi, I cancel out the h. Those are pretty intentional, and I'm left with, and you might not see this, but this is the electric field of a line of charge. Do you see that's almost the exact same? There are pieces that are different. One of the pi's canceled out because we're dealing with the volume of charge and not lambda. But everything on the top is a constant. And my electric field decreases as 1 over r, just like the line of charge. Which means the moment we're outside this thick cable, this thing has the exact same behavior as a standard line of charge. Questions about that? Yes, ma'am. This is the infinite sheet of charge. Yo. The infinite sheet of charge is the last one to do, and it's, again, there's a certain symmetry we're trying to use here to make the infinite sheet of charge work out for us. We're going to use sigma as the infinite sheet of charge, and I will tell you before we actually get to our solution that you should memorize this solution. The infinite sheet of charge is the building block of standard parallel plate capacitors. The electric field inside a parallel plate capacitor is based on the infinite sheet, and parallel plate capacitors form the basis for how we save and develop energy inside a capacitor. Understanding that electric field will be half of all the work we do with capacitors. So I would strongly encourage you to memorize the answer here and understand its meaning. Gauss's law requires that we have, again, some kind of shape, but do you guys recognize just from looking at this that the electric field is going to have this symmetrical outwards kind of detail? And similarly, it will have the same kind of electric field underneath. I just can't see those field lines because part of the sheet is blocking it. Does that make sense to all of you? So we can exploit that symmetry by choosing a shape that maybe sits, I don't know, with a little bit of the sheet both on the inside and outside. The general shape we tend to use is another cylinder, like a pillbox, that kind of pierces the sheet, with half of it lying on top of the sheet and half of it lying on the bottom of the sheet. This is the type of surface we tend to use. We try to make it centered so that this represents h, the height above the sheet, and there's an equal height below the sheet. And I'm going to make the top have area A. I could put pi r squared, but it won't matter. And here's why. Let's do the enclosed charge portion first. The enclosed charge portion is going to be sigma times A. That's got to be the Q enclosed. A is parallel to the sheet. Everybody understand why I said that statement? Because if A is parallel to the sheet, then every small piece of area of A is the same distance away from the sheet. Is that okay? So consider me just in on the shape for a moment. So I'm just looking at the top right now. There's going to be electric field here, electric field here, electric field here, electric field here, electric field there, and electric field there, and it goes on forever. But every piece of electric field pierces the top in the same direction. Is everybody okay with that? So when I want to find the flux, I'm going to have the integral of E dot dA for the top plus E dot dA for the bottom plus E dot dA for the sides. Okay so far? Now, do you all agree that the electric field is going to have to be the same value at each of these points? Does that make sense? They're all the same distance away from the sheet. So that means that that's going to be E times the integral of dA for the top plus E times the integral of dA for the bottom. which is just 2EA. Now look, I am one division problem away from the end, because this has to equal the enclosed charge. So when I put Gauss's law together here, Q enclosed equals epsilon naught times the flux. That'll be sigma times A equals epsilon naught times 2EA. The A's cancel. And the electric field is a constant. This is why we study the sheet. The electric field on either side of the sheet is a constant everywhere in space. All right, you guys have to go. And I'd like to for just a minute. It'll make this easier. Let's say that I have a couple of point charges. Positive Q, negative Q, and positive 3Q. So something non-uniform. And I choose a Gaussian surface like this, or a Gaussian surface like this, or a Gaussian surface like, let's be really obtuse, you know, all right, 3 different Gaussian surfaces. Do you realize that all of them must have the same electric flux? I mean, without even having to do any work, they all enclose the same charge. The thing about Gauss's law is, although it's bizarre when you first start looking at it, once you start to grasp the implications of what's happening here, some things become much easier to look at. So the electric flux here isn't any different for any of them. That doesn't mean the electric field is the same at any point. If I start picking points on this, so if I pick this point, the electric field here will be different than the electric field here, and it will be different than the electric field here. But what we're saying is, if you add up all the electric field over the whole area, the flux is going to be the same because the enclosed charge is the same. What I'm really trying to the ridiculous, and then there's, well,